This is the Triangle Inequalities lesson. And let's start off with a review of inequalities. Remembering that inequalities means not just equal. There's four cases. The first case is greater than. So here's an example. We've got x is greater than 7, which means that x could be 10 or 8 or 9.2 or 7.3 or infinitely many different possibilities. But it cannot be 7 or anything less than 7. The next case is the phrase is greater than or equal to. And the symbol there, we've got the p is greater than or equal to 13, which means that p could be 20 or 13 or even 17 or even 13. It could be the number itself, but it can't be 12.999 or anything less than 13. Our third case is the is less than. And we have the symbol there, r is less than 48, which means r could be 0 or 12 or 8.7 or 47.9 or 47.99 or 47.99999 and keep going on and on. But it can't be 48 or anything more than 48. The fourth case is less than or equal to. We've got h, and then the symbol is less than or equal to 23. And so some examples for h could be that it could be 3.8 or 14 or 22.85 or even the number 23 itself. But it can't be something like 23.1 or even 23.000001. It can't be anything that's more than 23. So that's our review of triangle inequalities. So of inequalities. So now let's look at this idea with triangle inequalities. And we'll do it by looking at an example. We're going to look at three different locations. We're going to think about the town of Novato, and we've got the town of Petaluma, and we have the city of San Francisco. And we could travel from Novato to Petaluma, or could travel from Petaluma to San Francisco, or we could even travel from Novato to San Francisco. And we can call those distances, we'll call the distance from Novato to Petaluma A, the distance from Petaluma to San Francisco B, and then the distance between Novato and San Francisco as C. Now, we could travel from Novato to Petaluma and then to San Francisco. If we did that, we would be traveling the distance A and then the distance B. But that would be greater than if we went straight from Novato to San Francisco. We could, on a separate trip, travel from from San Francisco to Novato and then to Petaluma. So we'd be going from San Francisco, then to Novato, then to Petaluma. So we'd be traveling C and then A. But that is longer than if we went straight from San Francisco to Petaluma. And on a third separate occasion, we could travel from Novato to San Francisco and then to Petaluma. So we start in the town of Novato, drive all the way down to San Francisco, and then all the way up to Petaluma. And that distance that we would have traveled is further than if we just had gone straight from Novato to Petaluma. I think it's pretty clear when we think about that, distances, because the shortest distance between any two destinations is a straight line, not going through something else like that. But this demonstrates these three things here. These looking at that as a triangle, the Novato, the Petaluma, and San Francisco as a triangle. This demonstrates what's called the Triangle Inequality Theorem. And the Triangle Inequality Theorem states the sum of any two side lengths of a triangle is always greater than the length of the third side. What the Triangle Inequality Theorem allows us to do is to play what is called the triangle game. And the triangle game is, given a set of 3 sticks, can you make a triangle? So here's our 3 sticks. I have one stick that is 5 units long, another stick that's 7, and a third stick that is 8 units long. Could you take those 3 sticks, put them together on a table, and make a triangle? Well, using the Triangle Inequality Theorem, we take the stick 5 and 7 and add them together and note, okay, that's more than 8, because 5 plus 7 is 12. All right? And then we take the stick 5 and 8 and add them together, and that is 13, which is more than 7, so that checks out. And then the sticks 7 and 8, and we add those together, we get 15, which is more than 5, so that checks out. So, yes, we can make a triangle. We know that we can win with that game. The question is, was it necessary to check all 3 situations? I want you to think about that. 5 plus 8 greater than 7. Do we have to add those two together to know that that's going to be greater than 7? We already know that 8 is greater than 7, so anything you add to 8 is still going to be greater than 7. And you also know that 8 is greater than 5, so anything you add to 8 is still going to be greater than 5. So we didn't really need to add all of those sides together. What did we have to add together? We had to add together the two shortest sides to make sure that the sum of the two shortest sides is still greater than the longest side. So that's something to be thinking about for this game. Here's the next set. We've got 3 sticks. All of them are 6 units long. Well, it doesn't matter which two I add together, since they're all 6. It's going to be 6 plus 6, and 6 plus 6 is 12, which is, of course, greater than 6. So I know I have a triangle. Not only that, but we should be able to recognize that we would have an equilateral triangle because all 3 sides would be the same length. And here is our third set of sticks. We've got a stick that's 7 units, another stick that's 3 units, and a third stick that is 4 units. And we check 7 plus 3, and that's indeed greater than 4. We check 7 plus 4, and that's greater than 3. But 3 plus 4, is that greater than 7? 3 plus 4 equals 7, and that's not greater than. 7 is not greater than 7. 7 is equal to. Since that's not greater than, you cannot make a triangle. And while I did check all 3 sets here of 7 plus 3 and 7 plus 4, let's go back to that very first problem where we said, was it necessary to check on all of them? No, we didn't. We only needed to really check the sum of the two shortest, 3 plus 4, to make sure that it was indeed greater than the third side. In this case, it was not, so we can't make a triangle. This elaborates the Triangle Inequality Theorem, which again states that the sum of any two side lengths of a triangle is always greater than the length of the third side.